All right, so we're going to talk now about the selectivity of halogenation. So you've already appreciated, right, that fluorination is too violent, and it's just too exothermic. And chlorination's pretty exothermic. Bromination's not very exothermic at all, and so we can control it. And iodination is endothermic, so we're not going to see that. Well, let's talk about what this means. How can we control it? So first of all, with substrates more complex than ethane, multiple halogenation products are possible, right? Because if you might have a halogenation here, which would be called primary, or you might have a halogenation here, which would be called secondary, right? And also note that there's a statistics game going on here, right? There's 6 hydrogen atoms here and 2 hydrogen atoms here. So if all these carbon-hydrogen bonds were equal in terms of both sterics and energy, then we would say that we would get 3 times as many halogenations at the primary as the secondary, right? Of course, there are other considerations. So let's talk about those. Chlorine is indiscriminate, and that means it doesn't it doesn't care where it goes. All right. So since secondary radicals are more stable than primary, the secondary halide is the major product, right? So you get 60% there and 40% there, but that's not very discriminate, right? We would like to get something better than that, because you might say, well, if I want to get halogenation, you really don't want a mixture of products. You really, as you're making things, you've got target compounds in mind, right? So to get mixtures are oftentimes not helpful. The hydrogen abstraction from a secondary carbocation is faster than a primary carbocation. We're going to spend some time talking about energy diagrams here in just a minute, but I want to sort of go over that one pretty quickly. Now, bromination is much slower, and since it's much slower, the more reactive secondary carbocation, we're going to get a lot more, right? 97% will go here at the secondary, and much less at the. Basically, we're going to get good yield, right? That's what we care about. Now, the fact that bromination is more regioselective, we can tie that back to something, and I want to spend a couple minutes talking about the Hammond postulate, right? This is something we learned before. Now's a good time to review it. It becomes exceedingly powerful in terms of just helping you understand why things are the way that they are. So the Hammond postulate, you recall, is that the transition state is going to resemble the reactant or the product that is closer to it in energy. So you see this is close in energy to the reactants. In bromination, the transition state is closer to the closer in energy to the intermediates, right? So the transition state is going to look more like a secondary radical for bromine, and it's going to look more like a not secondary radical, right? But rather like the reactants, which is just an alkane for chlorination. So here's a picture of that. Remember that if these two energies were exactly the same distance from the transition state, then this hydrogen would be exactly right halfway between it, right? Because it would be a mix between the two. But since the energy to this is closer to the reactants, this hydrogen is going to be closer to the way it looked when it was a reactant, right? And since the transition state of the bromine, this is the Hammond postulate, right? It's a good time to think about this. And if we talk about this, I don't know, a few more times, you could end up finding that it explains things for you, and you don't have to memorize. You have less to memorize, right? So our transition state here is closer to the intermediates because in energy, right? Here's the reactants all the way down here. Therefore, the hydrogen of the transition state is closer to that, and here, there's my transition. In the transition state, this bond is almost completely broken, and this radical feels like a secondary radical. Okay, so for bromination, the stability of the transition state largely depends on the stability of the resulting radical. For chlorination, it doesn't so much. All right, so in short, the difference in the transition state energies for the formation of primary and secondary radicals versus tertiary is much bigger for bromination, okay? And so bromination is much more selective in choosing the lower energy pathway, right? So the transition state, for example, here for bromination, you can see that's just going to be a lot faster. It's going to be a lot easier to get over that hump for a tertiary radical than it will be for a primary radical. And the difference, look at the difference in these activation energies, not nearly so much, right? And so it goes lots of different. You might get a primary, secondary, and tertiary. You're going to get a mixture. You're going to get a mixture with chlorine and less so with bromination, radical bromination. All right, so bromination at the tertiary position happens, look at this, 1,600 times more than at the primary position. So for chlorination, now we're dealing with a tertiary radical, right? For chlorination, we're going to get a 6535, which again is still not very good yield. But for bromination, it's 100%, essentially 100%, right? We get vanishingly small amounts of bromination at the primary position when a tertiary is available. Secondary, remember, for secondary it was 97 to 3, remember that? Right? But for tertiary, it's 100 to 0, essentially. All right, so if you want to make something with halogenation, your best route is to get a tertiary or a secondary alkane and halogenate with bromine.